Morning. So this is part one. This is civil engineering design of reinforced concrete columns, originally presented in 2006-7 by Dr. Colin Caprini, chartered engineer. So let's get straight into it. So for the design of reinforced concrete columns, introduction, background. The two main parameters governing column design are bracing. If the column can sway, additional moments are generated through the P delta effect. This does not affect brace columns, and the slenderness ratio, which is the effective length divided by the lateral dimensions of the column. Low values indicate a crushing failure, while high values denote buckling. So if you're not sure about this, I've done a lot more. There's a lot more detail about effective heights on in my steelwork column design videos. So if you want to know more about slenderness ratios, have a look through them. So in terms of the bracing, the two kinds of bracing are, well, what it really means here is that there's two kind of definitions of bracing. First one is braced, so you could have lateral loads on the structure are resisted by elements other than columns in the structure, i.e. lift cores, shear walls, maybe even sometimes diagonal bracing in steelwork. I've seen that before, just as steelwork, so you could also have that, but any other system except for the columns themselves. Hence, these columns mainly take axial load. However, bending moments may result in so this is the most important point. Hence, these columns mainly take axial load. However, bending moments may result in the columns due to unsymmetrical arrangements of loads. And the key thing you've got to remember in this is that with the reinforced concrete, basically all the joints are fixed, whereas in steel, when we were looking at steel, basically everything's simply supported. So you don't have, you've got moment maybe from eccentricity of loading of the load point when you've got like a fin plate, but basically these connections are all fixed. So when you look at analysis, you're looking at fixed columns. The beam is fixed at the column. But in this video, we're not looking at the analysis yet, we're just looking at the actual design of the section. So system condition 2 is unbraced. So these are lateral loads are resisted by the bending action of the columns. The axial loads are also taken by the columns, and you could have moments from the unsymmetrical arrangements of loading. So in the slenderness ratio is the ratio of the effective length LE to the lateral dimension of the column in that direction. We have two directions on plan, and we can have two ratios. Length of long side. So the length of long side of a column, when you've got a rectangular column, it's usually called H. That's the higher side. And the x-axis goes through the middle of H. So H/2 is where the x-axis is. So the slenderness ratio is the ratio of effective length to the lateral dimension of the column in that direction. We have two directions on plan, we can have two ratios. So the long side of the column, the slenderness ratio is called LEX/H, as per the little diagram here. The short side of the column, the slenderness, is LEY divided by B. So the B is parallel to H. The YY axis is parallel to H. The x-axis is parallel to B. So that's a standard column. The short side of the column, slenderness ratio, is LEY/B. So the effective length is calculated from a table in BS8110 and depends on the end conditions of the column for each axis. So the reason why we're trying to find this is that there's a definition. It's just going to come on to it, but I'm not sure actually if it says it straight away, but it's basically you've got two types of column, short and slender columns, and if the effective length over divided by the width or depth of the column is less than a certain value, then it's a different classified as a different type of column. But basically I'll talk about that in the next, a little bit longer, or in the next video. So the effective length is calculated from a table of BS8110 and depends on the end conditions of the column for each axis. So this is BS8110, there's an extractant it's clause number 38162, end conditions. Table 3.19, values of beta for brace columns is table 3.19, and table 3.20 is values of beta for unbraced columns. End conditions at the top 1, 2, 3, 4. End conditions at the bottom 1, 2, 3. End conditions at the top 1, 2, 3. Oh yeah, because you've got brace columns 1, 2, 3, and unbraced column unbraced column can be 1, 2, 3, 4. Basically, so you've got a cantilever condition. I might do another diagram with I think I've seen it somewhere else. There's a diagram that shows you all the end conditions. So 3.8.1.6.2 end conditions. The 4 end conditions are as follows. Condition 1: the end of the column is connected monolithically to beams on either side which are at least as deep as the overall dimension of the column in the plane considered. Where the column is connected to a foundation structure, this should be of a form specifically designed to carry moments. In condition 2, the end of the column is connected monolithically to beams or slabs on either side which are shallower than the overall dimension of the column in the plane considered. Condition 3, the end of the column is connected to members which, while not specifically designed to provide restraint to rotation of the column, will nevertheless provide some nominal restraint. Condition 4, the end of the column is unrestrained against both lateral movement and rotation at the free end of a cantilever column in an unbraced structure. So that completes page 4. So we have let's have a look at this. This is the failure modes. So we define failure modes. We define NU, that says, I don't know if you can see it, but it says NUZ. We define NUZ as the crushing load of a perfectly axial loaded column, and N critical as Euler's buckling load for the column. The following graph is typical and shows how for different slenderness ratios different forms of failure are possible. So 1, N critical over N UZ. So basically, if you have so it's saying that the following graph is typical and shows how for different slenderness ratios different forms of failure are possible. So L over H, basically when N critical, that's a Euler buckling load. So N critical, anything where N critical over N UZ is less than 1, it's crushing. Yeah. And when you've got L over H, then when the ratio N critical divided by N UZ, when that is more than 1, then it starts to buckle. So we see that here is the curve that basically says as the effective height of the column goes up. So it's done at L over H, but it's basically the same thing, isn't it? This axis along the bottom is the effective height, which is also related to the slenderness, because the effective height is the slenderness is effective height over H. So as the slenderness goes up, the column will fail in buckling rather than crushing, which is quite obvious, really, isn't it? The column will fail in buckling. Because the N critical value on the y-axis, underneath 1, when say N critical it starts at when you've got a very low effective length, then the column will fail by crushing, and as it gets longer and longer, it's getting slender and slenderer, then the column starts to fail in buckling. those where he's written crushing and buckling, that could be better put down there. So yeah, the relation is that as the column, it's basically very simple. As the column gets longer, then it's going to fail in buckling. So he's given some examples here. From the figure, for L over H equals to or less than 15, the crushing capacity is much lower than the buckling capacity, so the column crushes. For L over H is greater than 32, the buckling capacity is less than the crushing capacity, and so the column buckles. That's where he's marked on the two positions. For L over H, values in between the failure mode is not clear and depends on the imperfections in the column and the way the load is applied. So there's a sort of grey area here. So we might say crushing black, buckling white above 32, and then in the middle it's like could be either. Therefore, BS8110 defines short columns L over H equals 15 RC. Therefore, BS8110 defines short columns L over H equals 15 for a brace column and L over H equals 10 for an unbraced column. These ratios must be met for both axes. Send the columns, any column not meeting the criteria for short columns. As this module is short, we will only consider short brace columns. Short brace columns. In this video, we're going to do short brace columns only. So 1.2 is design aspects. At serviceability limit state, the actual compression needs to close up the cracks, which is beneficial. At SLS, the actual compression in a column tends to close up the cracks, which is beneficial. Hence, crack widths do not normally need to be checked in columns. Crack widths are checked in beams and slabs in water retaining structures and bridges, but don't need to be for columns. Further, deflection do not normally need to be checked in columns. It is ultimate limit state condition that govern the design of columns, i.e. their strength. So we just got a table here of bar of sizes. Areas of reinforcement are given for reference. So this is just a table of reinforcement areas, which you can find them anywhere. And then there's a couple of, we'll just do these graphs and then I'll finish the video, and then we'll do the next part will be short brace actually loaded column. So background information, we need to carry out a section analysis for columns just as we do for beams. So I've done that in another video, in my own videos of review section analysis for beams as previous columns, where I did all the K factors M over BD squared FCU. We need to use the material properties from BS811 as a reminder. We have Fy over gamma m tension, Fy over gamma m stress strain curve for steel from BS8110. So this is the reinforcement strength. Stress against strain. This is the yield. Fy is the yield strength of steel, and that the gradient is 200 kilonewtons per millimeter squared. Stress strain curve for steel from BS8110. Fy over gamma m. Fy over gamma m is, so it's equal. It doesn't matter if you compress it or you. It doesn't matter if it's in compression or tension. It's going to fail at the same value. Yield stress. So what he's done here is got what in BS8110. Then we've got stress strain curve for concrete from BS8110. So the most important thing as well now is to remember that in reinforced concrete design, tension of concrete is ignored because there has nominal value of tension. So on the graph we've got stress against strain, 0.67 FCU over gamma m. So there's another factor of safety here, 0.67. A parabolic curve, 5. And the gradient at the beginning is 5.5 FCU over gamma m kilonewtons per millimeter squared. And the strain is the strain 0.0. The maximum strain is 0.0035. And the strain where it flattens out is 2.4 times 10 to the power of -4 FCU gamma m. Stress strain curve for concrete from BS 8110. Remember that 0.67 is to relate cube strength to bending strength. Yep, and is not a factor of safety. Okay, so that was worth looking at. Let me just zoom into that one. FCU, 0.67 FCU. Now what I need to do, give a little bit more in the next video. I might add a note to this one. In the notes, I think I'll put in the notes that the strain, why the yield strain, because it's got there up to 0.0035, and then it's basically then it crushed, totally crushed. 2.4. I'll put some extra notes in there about that. So that basically concludes. This is going to be part 1. This is page 9 of 42, so there might be another couple of videos on it, but I think this video is getting a bit too long. Please like and subscribe to the channel, and donate if you can. Thanks for watching. Please tune in for the next video in this series.